We just finished up in the previous video talking about the refrigeration cycle and how that works and where the magic occurs. Let's keep moving on that, okay? So if I can get my slides to, there we go. All right, let me see if I can squeeze this down. So we'll come back to the camera here. Now, when we talk about refrigeration cycles, there's a quantity here we call the coefficient of performance, the COP. Now, notice it kind of looks like an efficiency, but it's actually not a true efficiency because this value can be greater than 1. So since this value can be greater than 1, we do not actually call it an efficiency. We save the term efficiency for things that are always less than 1. So because this can be greater than 1, we call it a coefficient of performance, but it still measures essentially the same thing. What do we want divided by what we have to do to get it? And in the case of a refrigerator, I have to put the work in. That's what I have to put in as input. What I want, what I'm desiring in the case of a refrigerator is I want to cool this low temperature space. So QL is actually what I'm after. That's my goal. That's my output. Now, there's nothing constraining or keeping this from being larger than that, so that we can't actually call this a true efficiency. In fact, in most realistic systems, ideally, we if at all possible, we do want this to be bigger than this, and that's the reason we use particular types of refrigerants is because they go through this process in such a way that a lot of times they allow this to be larger than that. Okay. Now, if you look at the first law for this system here, right? I think I can expand this out so you can see it a little bit bigger. So if you look at the first law for this closed cyclic system, right? If I look at my first law here, let me pull my pen up. I apologize. There we go. Okay. So what have I got? I've got QL going in plus work in minus QH. And that's equal to the change in the energy of my system. If it's a cycle, that's 0. So notice what I've got here. So this is my first law for that refrigeration cycle. And that's what it simplifies into right there. Work in is equal to QH minus QL. Okay. Now remember, in the previous slide, we introduced this idea of COP is QL over this work in. So COP for my refrigerator, for example, if that is in fact what I want, QL divided by the work net in to get it. And if I substitute this expression up here for that, now that is QL over QH minus QL. And then if I divide all three of these terms by QL, assuming QL is non-zero, then I get 1 over QH over QL minus 1. And that's how this equation then gets derived. Okay. Now, we're going to talk about why, Steve, why would we do that? Well, remember we talked earlier about efficiency for this heat engine, and we said the efficiency, we can derive it to be a function of the ratio of heat transfers. And we see that now with the refrigeration cycle. Now I've got the coefficient of performance for a refrigerator is also a function of the ratio of these heat transfers. There's a reason for that, which we'll probably get to in our next set of lectures. But before we get there, there's one more thing here that we need to talk about. Right? And that last thing we need to talk about is this concept of a heat pump. So a heat pump is when we use a refrigerator, a refrigeration cycle to heat up a space instead of cooling down a space. We basically repurpose our refrigeration cycle. So the story I always talk about in class would be, if you ever walk by an air conditioner unit, the outside part of an air conditioner unit in the summer, and while it's running, you feel the heat coming off of it, right? You feel this QH. Now, what if somebody walking by this in the summertime thinks, when it gets cold outside, I wonder what happens if I just turn this thing around right? And instead of pushing this outside, what if I in the wintertime, I push this inside, right? I use that QH to heat up the inside space instead of cooling the inside space. And that's essentially what a heat pump does. A heat pump is where we've taken a refrigerator and don't just take your if you're running a central air or I'm sorry, if you're running a window air conditioner unit in the wintertime, don't just take this thing and turn it around and run it that way. Some of some of your window units sometimes they'll have a heat option on them, and basically what it does is it internally switches the direction of flow around the other direction, and it'll actually do that the reverse for you. Um, and heat pump and large scale heat pump systems, they have some way of flipping the direction of flow to go the opposite direction internally. But really, it's the exact same device. You notice here the symbols are the same. It's the exact same device. Um, all you're doing is you're repurposing it. So with a heat pump, you're running a refrigeration cycle, and the only difference now is your goal. What you want is you're trying to heat the indoor space. And to do that, you're basically harvesting, you're stealing some heat from the already cold outside air. So let's say, for example, let's say you're just running all electric and you're running all electric heat and you want to heat your house. And let's say we're going to use 7 kilojoules of heat to do that. Well, if I'm running all electric, I've got to pay for all 7 kilojoules of electricity in order to do that. But if I've got a heat pump laying around, what I can do is instead of paying for all 7 kilojoules, I might be able to pay for 2 kilojoules of electricity and use a refrigeration cycle to basically cool the outside air a little cooler. And what I'm going to do is I'm going to remove 5 kilojoules of heat from the cold outside air. And I'm going to combine that with the 2 kilojoules of electricity. I'm going to put all 7 kilojoules of this together and pump it into the house um, just by basically running a refrigeration cycle in reverse, so to speak, or at least repurposing it. So it's kind of a nice, effective way of doing it. Here and again, we're in Oklahoma, and so um, the outside temperature sometimes gets so extreme that it's so cold that the refrigerant in the condenser, or sorry, the evaporator coils actually don't get cold enough to remove heat from the outside air on the coldest of days. So then this whole system just doesn't work, and then we're kind of in trouble. Now there's some solutions like putting heating coils on this side, and you can make it work. But anyway, it's really good devices for like temperate climates where your extreme temperatures don't get super extreme. But mathematically, it's the exact same. It's the exact same setup as what you have here. So mathematically, a heat pump is the same thing as a refrigerator, right? So as far as the mathematics go, your first law still looks like this. Your work in is still going to be QH minus QL. The only difference is how we measure its performance. The coefficient of performance for a heat pump, right? The coefficient of performance for a heat pump is what I want now is QH, and to get it, I have to put work in. And if I take this work in, QH minus QL, and I plug it in right there, now this becomes 1 over 1 minus QL over QH, as opposed to the refrigerator where the coefficient of performance for a refrigerator, we said that was what I want there is QL divided by work in. And when I massage that equation, this comes out to be 1 over QH over QL minus 1. But notice for a heat pump, right? It's same premise, it's just a different equation because what I want, my numerator, is a little bit different on the two. All right. And that brings us to an example, which is a nice stopping place. I'm not going to do that tonight, but that is the next place we go from here. All right, so good job so far, and we'll keep going from there.